Welcome to the dynamic learning hub of XLR at Andheri East. A prime spot conveniently located at just a 5-minute walk from LIC Andheri Metro. In our journey of over a decade, we have proudly trained over 2 lakh students. We've also been recognized by Deloitte, Silicon India, and other accreditation bodies. Experience learning like never before in our spacious and comfortable classrooms. With high-definition projectors and state-of-the-art acoustics in place, we ensure effective learning even to the farthest point in the room. The hybrid mode is a game changer as you can enjoy the benefits of a live classroom from the comfort of your home. Even if you happen to miss any classroom session, you can still attend the same session with the same trainer at the same time at your convenience, maintaining consistency in your learning progress. Wanna get started? Join us for a demo or career chat over a cup of coffee at our Andheri branch. XLR. We don't just train, we build careers.
Yes, so the collaboration with XLR was an excellent one. We conducted a Power BI workshop with Advanced Excel over a span of 3 days. The workshop was almost 12 hours long in total. Mr. Karthik, who was an amazing trainer, helped the students understand the concepts deeply. I am sure that the students will be able to apply these concepts in their careers as well as their daily lives.
The trainer, Mr. Karthik, was an excellent person where he explained in very detailed manner on how to give great insights using very complex data sets.
So it was a machine learning workshop. We learned a lot from the course and it was a great experience attending the workshop.
The trainer was very helpful. He had a hands-on approach with his teaching and it was fabulous.
This was a great experience for me. So I would absolutely love it if XLR and its team would come again to our campus and conduct more events like this.
It was a great course and it started from basics and took me to a great extent.
The experience of the workshop was really nice. The feedback from all the students was positive. They understood the concept. The workshop was also practical based with some questions. The experience with XLR was very smooth. They helped us in conducting the workshop smoothly right from the booking of the vendor and deciding the course till the distribution of certificates. In overall, this workshop was a success during our Technical Fest Atmos, and I thank XLR for being a part of it.
Good evening, all. I hope everyone is doing well. Guys, kindly confirm, is my voice audible? Okay, thank you for the confirmation. Okay, so good evening, Sunil sir.
Hi, Sushmita. Good evening.
Yeah, good evening, sir. You can start for the day.
Yeah, sure. Hi everyone. Good evening. So yesterday we were discussing about regression problem statement and some concepts related to AI and ML. And today we'll be working on classification problem statement. And I will take a data set and I will show you different steps in training the model and understanding what are the features that are impacting the prediction and what are the features that have more significance towards making the decision so that we can provide that information to the consumer who will be consuming our models. And apart from that one, I will try to explain to, I mean, today I prepared to explain you two algorithms because I'm not sure whether you have knowledge about how these algorithms work, because if you know how this algorithm works, then you will be able to understand what I'm trying to convey. Like for example, if I'm saying hyperparameter tuning, you need to know why I need to do hyperparameter tuning, and to understand why I we need to do hyperparameter tuning, you need to understand how the algorithm works. So for that one, what I did for today is today I selected logistic regression and random forest as the algorithms, which I will try to explain how they work as much as possible. And then we perform hyperparameter tuning as well. And once we do hyperparameter tuning, we try to find out what are the best features that are impacting that are helping us in predicting the target variable. And at the same time, today I try to build sharp plots. I will try to build sharply plots, which are generally used to explain the model, are used in model explainability, and it's widely used in industry, and which might be helpful for you if you understand this concept. And I try to explain you some of the hyperparameters in logistic regression as well as random forest regression while working on the project itself. And along with that one, I will be discussing about different performance metrics which will be used in classification problems, because until unless you understand these metrics, you will not be able to understand why we are using a particular metric and and in any problem statement, and what is the significance of the results which we understood from the model. And in order to communicate to the stakeholders, we need to have a report prepared to make them understand what is happening with the data, and what are the results that we think might help the consumer to make his business decision. So we'll be discussing about that particular performance metrics as well. I will try to give a glimpse about that values also. So yeah, let me share my screen and start with the data set. Today, to explain this one, I will be using my Visual Studio Code. So yesterday we were working on Google Colab, but I thought like some of you might be more familiar with VS Studio Code. So I'm using VS Studio Code today to explain you about this particular problem statement. Just give me a second. I will share my screen and you'll be able to see that. Uh, I hope you can see my screen. If you are unable to see my screen, just drop a message. So today, the data set which we are going to use is credit card fraud prediction data, which I download this from Kaggle datasets, and then I'm using this data set to make predictions about whether a particular transaction is fraudulent transaction or not, based upon various features. One important thing in this data set, first I will show you the data set and then I will try to explain you what the data is. So if you look at this particular data set here, you will be able to see multiple features. The features which we might know is the time, and the other feature which we can understand from the data set is, the amount, which is like what is the money or amount transaction that happened in the particular transaction, and the class. Like for example, if it's a zero, it's a non-fraudulent activity, and if it's one, it will be fraudulent activity. But if you look at these features, V1, V2, V3, so on, so to up to V28, the features we don't know the features because most of the banks or most of the financial institutions will not be ready to give any of this any of the data because they are more that data is like I mean they are not supposed to give any data that is related to consumer to any of us. I mean, like even like for example, if we are working for a service based company which is providing services to an financial institution, they are not supposed to give the data directly, and in order to secure the data they will give data with some different names which doesn't have any meaning, or which will be given with some notations. And in this case, what they did is like they did principal component analysis, and these particular features are principal components that are regenerated by using the data that was by using the original data that was available with the financial institution. I will try to cover this principal component analysis tomorrow so that you will be able to understand what is this principal component analysis and what happens in principal component analysis. Principal component analysis comes in one of the technique which is used for feature selection or feature engineering, and it's most widely used technique along with LDA, linear discriminant analysis. So I will try to discuss that one in the next 3 days. I will create some time. I will try to discuss that particular part in next few sessions. So for the time being, consider that these are the features which are anonymous to us. We don't know what that feature is and what that feature signify because they are not going to give that data directly to us. And now we need to use this data and then build a model which will try to predict, given certain features, whether that particular transaction is fraud transaction or not. For your convenience, I have provided some information here about the data. So we have total 31 features and one target variable. Our target variable is the class. If the class value is 1, that means the transaction is an fraudulent transaction. And if class value is 0, then the transaction is legitimate transaction. That means it's non-fraudulent transaction and it is a genuine transaction. So the time represents the elapsed time in seconds since the first transaction. So we try this time will give us this time value is nothing but number of seconds between two transactions. So we'll be using that as a feature. And V1 to V28 are anonymized features, which are nothing but principal components. And I mean, they are like I mean, they come from different set of features. It might be combination of features, or it can be features which are anonymized. It can be anything that is available with their data, and amount specify the transaction value, and the value here is in US dollars because the data set belongs to US transaction data. And as I already explained, the class denotes whether a transaction is fraudulent transaction or not. So we'll be using this data. So when we start with working with the project, we will not be having any libraries with us. So we need to first install all the libraries. In Python, we'll be using pip install to install all the libraries which we need in order to train the model. So here I'm trying to use pandas, NumPy, scikit-learn, and matplotlib, Seaborn for visualizations, and Sharp for model explainability. And I'm using IMB learn for imbalanced data sets to balance the data. And that is one other important thing which we'll be discussing in this class, because when it comes to classification problem statements or regression problem statements, supervised learning, one of the major problem is imbalancedness. So we'll be discussing that as we proceed towards this problem statement. Okay. So yeah, the first step once we receive the data is importing the necessary libraries. As I already mentioned, we'll be using NumPy, and just a minute. Yeah. So sorry for that. We'll be using NumPy and Pandas for data frame operations, and scikit-learn for training the model, and Matplotlib and Seaborn for visualizing the data, and Sharp for model explainability, IMB-learn for creating synthetic data to balance the classes here. So first thing is I downloaded the data and I kept in this particular folder so that I can use that one. And today also we'll be dealing with CSV file. And so I'm loading my data using read underscore CSV method. And once we look at the data, we can understand how many features are there, what are the features, and what is the data that is available in this particular data set. So this is how we can this is what we can understand from this data here. And once we load the data, we need to understand how the data is distributed, or what is the feature of the, I mean, like, what is the information related to this particular data set. And at the same time, we need to understand statistical importance of different features and statistical information about features as well as our target. So next few steps we'll be trying to understand how the data is distributed, and different statistical values for different features and target variable in this particular data. So the first step will be like we try to extract the information about the data, like how many data points are there, how many features are there, and what is the data type of each feature, and what are the total count of null values within is there are there any null values in the data set, and if there are null values, what is the total number of null values that are available in the data set. So that's what the information we are trying to understand here, because based on this information we will plan our next actions, and we use that information to plan the next pre-processing steps. So by looking at this data, we can understand like every data that's being represented, that is represented effectively and accurately, because we can look at this data and we can tell like all the feature columns are numerical, provide numerical information. And if we look at this particular information also, we can understand that they are represented effectively, and the target variable contains only 0 or 1. So that is being effectively represented through integer value. And if we look at all the features, there are no null values, and we have total of 31 columns, including the target variable, and we have around 284,000 data points here. So this is the information which we can derive from the data, and now we are trying to see if there are any null values or not. There are no null values here, so we will not be dealing with any imputation at this point of time in relation to this particular data set. And now comes the class balancedness. This is one of the major problem you will be facing in supervised learning in general, but particularly this is one of the major problem you will be facing in most of your classification problem statements. And in real, I mean, if you ask me in real time, I faced this problem in two of my projects. Both are classification projects, and I have faced this imbalanced data problem in two among five of our projects I worked with the company. So both of the project has this imbalanced data problem. So you can expect this problem when you start working with a company. So the imbalanceness is nothing but, let's say in this case, we have two classes. One is fraudulent class, and another one is non-fraudulent class. So in general, when you look at transaction data, or when you look at any transactions, the number of transactions that involve any fraudulent activity will be comparatively low when compared with non-fraudulent or genuine transactions, because majority of transactions will be genuine, and very few number of transactions will be having some fraudulent activities. So what happens is like, when we have thousands of the ratio will be in such a way like for every 1 lakh or for every 1,000 transactions, the possibility of a transaction being fraudulent will be 1 or 2. So this is the ratio between a fraudulent class and non-fraudulent class. And because of this, what happens is like, when we have more number of one class, which is called as majority class, the model, while training the model, will try to understand or understand the patterns which are available, which are more towards the majority class, and ignores the minority class. And what happens is like, the model will have the best metrics and will be able to have an accuracy of 99%, But what happens is like if your data set has one majority class, like for example, let's take 100 data points. I mean, for our analysis, assume that you have total number of total 100 data points, and the majority class is having 98 data points, and then minority class is having only 2 data points. So what happens is like the model will be able to understand the majority class effectively, but the minor it will not be able to deal with minority class effectively. And when you look at the metrics, your metrics will show around 98% accuracy. So what is happening here is whenever you give some data, it will be right 98% of the time, because 98% of data belongs to majority class, and for all the minority class, it makes error. Even though it is making error for both these data points in minority class, still the accuracy value for your model looks around 98%. So which doesn't make any sense, because the model is not doing anything but randomly predicting every class as majority class. Like let's say for example, our majority class is fraud transaction, non-fraud, genuine transaction, legit transaction, and minority class is fraud transaction. So among 100 data points, we have 98 data points as legit transactions, and 2 data points for fraud transaction. So even though if instead of learning something from the data, if model starts predicting only legit transactions, still your model accuracy will be 98%, because it is making only mistake only in 2 cases out of 100 data points. So that's what happens when we have this imbalanced data sets. And what happens is like model will not learn anything, and it just randomly gives you only one response, that is legit transaction for every transaction. And you will be missing the important thing, that our main goal is to differentiate a transaction from fraudulent to differentiate a fraudulent transaction from a legit transaction, which is not happening in this case, because our model learned only this particular legit transaction, and because the data points which we provided for training has more number of legit transactions, and it understand the legit transaction effectively, but it was not able to understand the patterns in fraudulent transactions. So that's the major problem in imbalanced data sets. So that's why we try to deal with this problem before we train any machine learning model. So in order to understand the class imbalanceness, we try to find out what is the class distribution, or what is the target variable distribution, target value distribution within the data set, and then we try to see how they are distributed. If you look at here, what I'm trying to do here is I'm trying to calculate I'm trying to calculate value counts for each class. As the problem statement is a binary class problem statement, here we'll be having 2 classes, and we are trying to see what is the total number of data points that are available for each class. And now I'm trying to make it easy for you, or to visualize it effectively. I'm trying to create this plot from the information that I'm getting from this class counts, so that we can understand what is happening within this data set. If you look at this image here, we can see that out of what the total number of data points we have around 2,84,807 data points. And among 2,84,807 data points, we have 2,84,315 data points as legit transaction, and only 492 for fraudulent activity. Just imagine what is the ratio of this particular. Let me check what is the ratio of this particular. Say, just a second. Let me calculate what is the ratio. P2 divided by. So it's around 0.001727%, which is like very. I mean, it's like around 0.17 or 0.2 percentage of data belongs to fraudulent transactions, and rest of the data will be related to legit transactions. So if our model, I mean, when we train the model with the same data, and if our model starts predicting legit, the accuracy will be like, I mean, I guess you guys know how this accuracy is calculated. The accuracy is calculated using the equation like predicted total correct predictions by total number of predictions. So here, if the model predicts all the 2,84,315, I mean, like if the model starts predicting only legit transactions, like whatever the data you give, if it predicts legit only, what happens is like it will be right almost 99.8% of time, because only 492 cases are wrong. I mean, it will be wrong only in 492 cases, which comes to an average value of 0.2 percentage. That means it is always correct in the accuracy will be around 99.8%, and we will think like the model is performing very well because 99.8% is one of the best accuracy any machine learning model can give. And we can look at that value, and we can get misled by the information, by the accuracy values from the model, because the data is like that, and we haven't done anything in order to avoid this particular scenario or this particular issue that is there with the data set. So that's why before training the model, we need to first deal with this particular imbalancedness of the data. So in order to deal with this one, we need to we will be having multiple ways to deal with this one. Anyone have any questions so far? Or, and if you have any questions, just you can drop a message here. Take it as a no. I hope everyone is clear with what I explained so far. So by looking at this data, we can understand like the data set is highly imbalanced, because for class 0, which is a legit transaction, we have a higher number of data points, and for class 1, which is a fraud transaction, we have very less number of transactions. In order to deal with this problem, we have multiple techniques to deal with this particular problem. So what we do in this case is what we can do is we can reduce the number of non-fraudulent transactions and make this equivalent to this particular number of transactions, and use that data set to train the model, so that the model will now be, I mean, the data will now be balanced data, and model will try to understand the hidden features or patterns within the data. And now what happens is like, as the data is evenly distributed across two different classes, it will try to understand the patterns or the features or the patterns which make any transaction either fraudulent transaction or non-fraudulent transaction. So that is one way to deal with this imbalanceness. RS, and the problem with this kind of solution is like, instead of, even though we have around 3 lakh data points, we are still using only less than 1,000 data points, which is less than 1% of data. So data is, I mean, you might have already, I mean, everyone might have heard that data is currency, and in spite of having data with us, we are still not able to use that amount of data because of this technique which we followed. So that is like wasting the data. And at the same time, even though we select this data randomly, we might miss some patterns because out of 2,84,000 data, we are just selecting 0.5% of data, not even zero point 0.5, it will be around 0.1% of data from the total data from legit transactions, which might not be an accurate sample, even though it will represent, it will be a sample that will represent the legit transactions. Still, what happens is like we might be missing some patterns within the data, because we are taking only a subset of the data, and some hidden patterns might be available in the data which we are not using. So that is one of the major problems that we can face by following this technique. In order to avoid this issue, there are other techniques where we will try to oversample this particular class by using an algorithm, and then oversample this data to meet to reach closest to this particular value. So that what happens is like we are synthetically generating data for this second class as well, so that the data will be equivalent to the second majority class as well. And then what happens is like, instead of losing the data, we are trying to create more data and then use that data to train the model, which will be more effective when compared with losing the data from the data which we already have. So that is another technique where we create synthetic data. There are like the techniques like SMART, which will oversample this minority class in order to match it with the majority class. Or what we can do is like we can use class weights in order to train the model. What happens is like instead of directly training giving equal weights to both the classes, we will assign different weights to these classes, and then we train the model so that the model will understand like within the data this particular class is having more amount of information, and this particular data this particular class is having less amount of information. So give more weightage to this class and less weightage to this class, so that the model will try to understand the patterns that are available for minority class as well. So there are different techniques which we try to deal with this imbalancedness. So we'll be using both the approaches to train the model. So for the first approach will be like reducing the sample data points for legit transaction or majority class to match the minority class, and then use that data points that are available with this, and then train the model. So here what we are trying, I gave this notes for you to understand what is happening in this particular cell, because what we are doing is we are creating a subset of data from this entire legit transactions, and using that to match the particular value, and we are doing this random we are taking the samples randomly, because if we take initial few number of data points or last few number of data points, or if we manually select, what happens is like it might create some kind of bias in the model, and the model will not get trained effectively. So that's why what we will do is we will be doing random sampling, and we take random data points from the data, and then use that as a subset of data and create a new data frame. So here what we are doing is we are creating this legit data frame by creating a subset of data. And so if you look at this one to understand how these particular legit transactions and fraud, to get statistical information about these legit transactions and fraud transactions, we are creating two data frames from legit transactions and fraud transactions, and then trying to see what are the statistical information about this particular two classes. And first we'll try, before we go with balancing the data, let's understand the significance of, or statistical significance of each of these classes. So if you look at this value, what we are trying to do is we are trying to understand the value of amount in both the classes. Like for example, if for legit transactions, what is the statistical information that is available for legit transactions, and what is the statistical information that is available for fraud transactions. If you look at this case, you can see for legit transactions the mean value of amount is 88 USD, and standard deviation is 250, while 75th percentile is 77, and 50th percentile is 22, which is nothing but minimum value. And this 25th percentile is having 5.65 as value, and the maximum value in a legit transaction is 25,691 USD. And similarly, you can look at fraud transaction here. I gave some notes to understand what are these statistical information that is available in this particular cell here, because you need to know this information in order to make any judgment, or in order to provide, or in order to interpret the results, or in order to provide some information to the business analyst, or the consumer who will be using your reports. So here you can see like this count will give total number of rows. I mean, it's like nothing but total number of data points available for that particular class, and the mean value will represent average transaction amount across all the transaction for that particular legit transaction, which is around 88.29 US dollars. And the standard deviation is one of the measure which will explain the spread of transaction amount, like how the values are spread. I mean, with the highest standard deviation, what happens is like the data is spread across wide range, and if the standard deviation is low, you can understand that the data spread is comparatively low, which is not spread too much, and which is more concentrated towards the mean or median values. And 25th percentile will give as the information about all the values which fall below 25%. If you have seen the bell curve, which is generally used in this normal distribution or in probability distributions, you'll understand this 25th percentile and 50th percentile. I will try to add that bell curve as well within this, and before I provide this notebook to you. The median value is nothing but the middle value of the transaction amounts, and we try to calculate what is the middle value within the transactions, and then try to see where the middle values are more focused, and then 75% will give you all the values below 75% of the transactions, and the maximum value is the highest value that is available in amount for legit transactions. So the similar way we are trying to understand the distribution of fraud transactions. If you look at these cases, the mean value for fraud transactions is 122, whereas 122 USD, whereas for for an legit transaction, the mean value is 88. You can understand, like, I mean, we can generally understand, like, anyone who does a fraud transaction will try to extract as much as possible. So in that's why in general, most of the data points in fraud transaction can be, I mean, the possibility of most of the transactions in a fraud transaction will generally be on higher end, and that's why we can see the mean value as higher value, whereas standard deviation is same for in both the cases. And if you look at this one, only very few less amount of information is available in 25th percentile, because 25th percentile is lesser value, and even the in the middle value also the values are comparatively less when we look at the similar pattern in this particular legit transactions. But whereas when it comes to 75th percentile, majority of we can see that the value of 75th percentile is higher when compared with this particular legit transaction, because as we already, I mean, as I already told you, the most of the transaction fraud transactions will try to extract as much money as possible. So this particular values in higher, the values will be in general will be in higher end, and they will try to extract as much amount as possible. But whereas the maximum amount is comparatively low, but most of the transactions will try to extract, because in general everyone, most of the transaction legit transaction, what happens, like, they will withdraw very few or very less amount. Like, for example, if you have some requirement, you will draw 100 rupees or 200 rupees or 1000 rupees or 2000 rupees, but the amount of transaction where you withdraw 1 lakh rupees or 2 lakh rupees in general will be comparatively low, because the number of people who withdraw that amount will be very less, and the frequency of withdrawing that amount will be comparatively less. So that is being reflected even in this case, because the frequency of higher amounts in fraud transactions is comparatively high, which can be observed from this highest value for 75th percentile transactions. So that is one information which we can understand from the probable this statistical information that is available with us. And then to understand across that, to understand the mean values for all these features for different classes, like for example for legit class how the a particular feature is varying, and for fraud class how a feature is varying. I created this group by class in order to understand how every feature is varying for different classes. You can look at this and you can understand there is significant difference between most of the features. If you look at this case, the time between two different transactions in legit class is around 94,838 seconds, whereas in case of fraudulent activity it is comparatively low, it is 80,746 seconds. And even if you look at these features, anonymized features, you can look at this in case of legit transaction the value is around 0.008, whereas the value is minus 4.77. Similarly, you can look at these other features as well. You can find significant difference between these two. From this we can understand that when a transaction, I mean, we will be able to understand, like, we can differentiate these two transactions, and data is effectively distributed in such a way that there is a pattern or there is an plane or something which will separate these two transactions in majority of features, and we will be able to train a model effectively which can understand these hidden patterns, and we'll be able to predict any transaction as a fraud or legit transaction by looking at this information as well. Because when we know that there is difference in different features for different classes, we know that the pattern they are follow the features are following is different for different classes. So that itself will tell us like, okay, there is difference between how a particular feature is operating for different classes. So that is one of the important information which you can derive from this particular cell. It will give you like what is like how the particular how these features are varying across the classes, and even you can see that reflected in amount as well, so the mean amount as well. So in order to understand this effectively, I mean, by looking at the values you might not be able to understand this effectively. So what I try to do is I try to create plots for different features, and to look, I mean, see, giving looking at the numbers, and any business analyst or any person who is a consumer might not be able to understand effectively what is happening or how the particular result, I mean, how to interpret the results. So in order to make that easy for them, what we are trying to do is we are trying to give this visualization to them, so that what they can do is that they can look at this and they can understand like what is happening. Okay, is there any difference between any class? Like for example, we can understand like the mean value for time is higher for legit transaction, whereas for for this fraudulent transaction the mean value is comparatively low. And we can find okay, that means time that the time between two transactions is having significant impact on understanding a particular transaction is fraud or not. Similarly, the mean amount value is also having significant impact, can have significant impact on making a particular prediction as a fraud transaction or a legit transaction. So this will help them in understanding this. And I intentionally created this one in a single plot, because if I create multiple plots, it will go to 30 plots and it will be clumsy. So you can look at this one here also. You can see for every class, you will be able to understand there is significant difference for both these values. Like for example, this particular V1 class, if you look at this particular V1 class here, the value for V1 class at most is around 0 point something, and whereas when it comes to fraudulent transaction class, the V1 value is most of the times it is negative values. So that means it indicates like if the V1 feature in general falls in a cat value ranging from 0 to negative values, then we can the possibility that that particular transaction is fraud increases. So that's how they can interpret these results, and this particular plots will be of highly helpful for them to understand how each feature can help us in understanding these particular classes, and at the same time how the features are distributed across the classes. Any questions so far before we go with how to deal with imbalanced data sets? Anyone, any questions? Does what I'm saying makes any sense to you? Like, does it make sense? Do my explanation make any sense to you? No response. Can I consider that as no doubts and you understood everything effectively? Okay. So now let's go to imbalanced data sets. So as I already mentioned you, imbalanced data sets are one of the major problem that faced in data science, in I mean data science field. And because as I already mentioned you, the majority class will dominate the minority class, which will cause poor model performance. Even though it might, I mean, the metrics might look good, but the actual performance of the model will generally be very poor. Like for example, let's take the email classification system. So if you receive around 1,000 emails on a day, the number of emails that will be marked as spam will be at most 10 to 20, because the number in general will be comparatively low. So when you have 1,000 emails, trying to understand the patterns with in 990 emails is different when compared with understanding patterns with 10 emails. So that's one major problem, and this particular problem is more significant in case of classification problems, because here we will be having minority class and majority classes, and when we are unable to predict minority classes, and in most of the cases in classification, and particularly in case of imbalanced data, our prime importance will be minority class. For example, let's take if a person gets a disease or not, the persons who will get the disease will be a minority class, and who doesn't get a disease will be majority class. Or when you take this email spam classification, or fraud transactions in financial institution, and even if you take, if a particular consumer will turn into business or not, what happens is most of them will not turn into business, and very few of the calls will turn into business. So in most of the cases, even the cancer detection cases, like for example, you have an MRI report, or X-rays, or there will be different kind of reports which will be used in computer vision to try to understand the tumor, and then the data which is already available for healthy patient is comparatively very high when compared with data that is available for the patients with the tumor. So the here the problem is when we have minority data class, our prime target is like, even though if we predict a particular person is having disease, at most thing is like he will go for another round of screening, and he will be, I mean, if we make a mistake here by telling and a person who doesn't have a disease like as having a disease, and what happens is like we will send him for the next screening, and in next screening he will be able to we will be able to understand that the person is not having disease, and we can avoid the situation. But just imagine if we make a mistake in case of minority class, like for example, predicting the particular person is not having disease, even though he is having disease. What happens is like we are skipping the person from the treatment, and this is more problematic than the first case. So that's why in most of the cases, our primary our important class is the minority class. Even in case of fraud transaction also, even if we mark an legit transaction as fraudulent, at most what happens is like we will receive a call from the customer, and he will ask us like, this is a genuine transaction, why do you block my card? But if we miss this fraudulent activity, what happens is like the consumer will lose money, and it will be the biggest problem, and we need to pay money to the consumer, to the bank customer. So that's why in most of the cases, minority class will be more important, and our primary focus will be to improve the prediction accuracy towards the minority class. That's why they're dealing with this imbalanced data set is of highest concern. Please let me know if you have any question related to the explanation which I gave related to majority and minority class, and why we focus on particular class, because you will be asked questions in related to this one, like what is the parameter or what is the metric we need to focus when we have this problem statement. Because we don't use accuracy when the data is imbalanced data, and we try to use another metrics in classification while we are dealing with imbalanced data, because and depending upon what class we need to focus upon and what is important to us, we will change our metrics, and we will report that information based upon that one. So I guess there will be I mean, you face any very less data science interviews without this particular question. You will for sure receive a question related to this classification metrics, and the terms precision and recall and F1 score, and imbalanceedness as well, and these classes, majority and minority classes, in most of your interviews. So if you have any question, you can ask me. You can drop a message if you are unable to mute yourself. Okay. So now you understood the problem with imbalanced data. So now let's go ahead and how to deal with this particular imbalanced data. As I already told you, one is random sampling. Like what we're trying to do is we'll take equal samples which match with minority class. I mean, we are taking random number of samples which is equivalent to the number of samples in minority class, and use that data to create a new data frame, and use that to train the model so that the number of samples in majority class matches with minority class. But the problem is we are losing data here, and data is of highest significance in data science or machine learning or AI or any of these fields. So that is one way to deal with this imbalanced data. So ideally what we are doing here is we are undersampling the majority class, and another way of the dealing with this problem is oversampling of minority class. What happens is like we create synthetic data to match in minority class, and they try to match that particular try to match the number of data points in minority class with that of majority class, so that both the class are close enough to, and to make ensure that the model will understand the hidden patterns in both the classes. So the problem here is we can in this case what happens is like we are randomly duplicating the data. That means in oversampling we already have data, we already have 492 samples, and we change the data randomly like this, and we are duplicating the data, and we are creating duplicated information, and we are increasing the number of samples to from 492 to 2 lakh something to match this particular majority class. But the problem is we are creating a lot of duplication here, and this will lead to overfitting of the model, because as we keep on duplicating the same features, that particular feature will gain a lot of significant importance, and it tries to overfit the model, and this will in turn cause create problems. So that's why this oversampling is generally not preferred, but you can see that this being used in some cases. But there are some advantages to this one, like it's easy to implement, and it's very easy to do this case. But the problem is undersampling results in loss of data, and oversampling will lead to overfitting, because we are repeating the samples, and at the same time automatically what happens is like we are indirectly giving more thrust on the information which we have in minority class. So obviously it will lead to oversampling of information. So before we go with this mode, let's train the model with the first case, where we try to undersample the majority class to match with that of minority class, and try to train a model and see how that particular model performs. So here what I'm trying is I'm trying to create a sample of data, random sample of data. When we use this method, it will randomly select data from the available class, and with the total number of data points as mentioned here. So we take that sample and then create a new data frame by concatenating the fraud data which we created earlier by separating it from legit transactions, and then concat these two to create new data frame. And if you look at this one, as we are creating only 492 samples for legit, and we have 492 samples for fraud transactions, the total number of data points will be a summation of 492 plus 492. It will be around 994 or 984. I guess it will be 984. I'm not sure. Yeah, 984. So this will be the new data frame which is created by undersampling the majority class here. And here now you can see the value counts for both the classes, which is equal, which is 492. And even in this case also, I mean, to understand, we might have the question. As I already mentioned you, sometimes what happens is like when we undersample the majority class, we might lose some information. So that's why I'm trying to see, is there some information which I am missing from the data. So in order to do that one, I'm trying to do this group by, and trying to see if mean value for this sample is representative of mean value for the entire legit data frame which I created earlier. So if you look at this one here, the feature values are like this, and if the particular mean value matches with this one, then we can consider that okay, the new data frame which is created by undersampling is closely resembling the information that is available here. So by looking at this, we can say like it's closely resembling, I mean, it's almost same like what it has been doing, because when we try to create the sample, it tries to keep the particular, it will select the data points in such a way that the mean values for all the features are the probability, sorry, a statistical distribution of all the data points for the sample closely resembles that of actual data set. So that's why we can see like all the features matching closely with the actual values of actual data set. So now we can go ahead and train our model. So while training the model, we need to separate our feature variables from our target variable. So now we are creating a new data new data frame by dropping our target class here, which is nothing but our features which will go into training of the model. And then we are creating our target variable here, which is nothing but class column in our new data frame. And then we are creating this test train split data. That means what we are trying to do here is we are trying to remove some data points from the data randomly, from the data frame which is available with us randomly, and keep that aside so that the model will not have any look into this data, and it will only try look into the data or look into the patterns that are available in the data from this particular only from from the data which we selected for training. Like for example, here I am taking 20% as a test size. That means 80% of data will be used for training, and 20% of data set will be used for testing. So what happens is like among these 984 data points, 80% of data, 20% of data set points will be removed and kept aside, and remaining data points will be used for training the model. So what happens here is that that 20% of data points will not go into training, and they will remain aside until the model is trained. And once the model is trained, we will try to see how the model is performing on unseen data, because this particular test data was not yet exposed to the model. So obviously this is some new kind of data, and we try to see how well the model is predicting with this unseen data, so that we can have an estimation that in future when we receive some unseen data, the model prediction will be close to this particular predictions, which I mean the model accuracy will be close to the accuracy which it made in this particular test data. So that's why we split the data into this one and train the model. So here I'm using a logistic regression model in order to train the model, which is simplest model for classification. And I'm calling this logistic regression model here. And then I'm using my X-train and Y-train data to fit the model, because the model here is logistic regression. I'm fitting logistic regression with this X-train and Y-train, where this logistic regression model will try to understand the hidden patterns, and it will come up with the coefficients in order to train the model. And then we are trying to this here what we're trying to do is we are trying to predict for model and trying to calculate accuracy, and this accuracy score is calculated for this training, and we are displaying what is the training data accuracy. So here you can look at this accuracy value, which is 94.5%. So it's fraction value. So if you want to have the percentage, you need to multiply this by 100. So it is 94.4% accurate. That means when you pass 100 data points to 100, when you give 100 samples to the model, if the model predicts 100 samples, then it will be right 94.4% of time. So that's what this accuracy tells us. But our major focus is not on training data, because the model has already seen this training data, and because it already knows what is y train. That means what is our target variable for given this feature. So it already knows that information. So our primary focus will not be on this training data, but our primary focus will be on testing data. Here, what we do is we don't give what is y test. Here, if you look at this one, while training, we are passing feature as well as the target variable to the model, so that when the feature is like that, what is the target variable? When the feature is like that, what is the target variable? So that the model will try to understand the hidden patterns within the training data. And when we try to predict, what we do is we just give the features. We don't pass this target class from the test data, because we don't want the model to look at that and look at the class variable and tell us that this is the class for this particular feature. We want, what we want is we want the model to do this one. So that's why we are not passing that Y test here. And we collect these predictions for the 20% of test samples which we kept aside. And then we try to calculate using these predictions and with actual value. That means this is the prediction made by the model for a particular feature set. And this is the actual Y test value that is available for that particular feature set. And then we are calculating accuracy, and here you can see like the model is correct 92.8% of time. That means if the model is making predictions on 100 sample points, it will be right 92.8% of time. That means out of 100 it will be correct, it will give accurate predictions for 92.8 transactions. So that's what this accuracy indicates. And these are other metrics which we will be discussing in some time. So the classification report, confusion matrix, accuracy score, which we already calculated, and will be calculating F1 score, precision and recall, and we try to see what is the precision and recall values. You can see here the precision value for 0 is 0 0.9, and precision value for 1 is 0.97. Recall values are this one, F1 score is this one, and then this is the confusion matrix. You might have heard about this confusion matrix, where we try to understand what is true positive, what is true negative, what is false positive, and what is false negatives. All this information will be understood by confusion matrix, and this is one of the important metrics which will be provided to consumer while working on classification problem statements. So this is how we train the model here. This is what happens when we train without we are undersampling here, and then we train the model. Now let's see the other approach where we try to what are the other ways to deal with this particular oversampling. Give me 2 minutes. I will just have some water and come back. If you have any questions, please drop here. I will respond to that. Yeah, sorry. So now to understand different other techniques for dealing with this imbalanced data set. Um, so there is synthetic magnetic oversampling technique, which will oversample the data. But here we are not randomly or duplicating the data. We are trying to create synthetic samples by understanding the patterns within the data, and we create new data points by using this. We create the synthetic new data points by using hidden patterns within the data and oversample the data so that. It will be able to reflect actual patterns that are available within this minority class. Like in some cases we can use, I mean, ideally what we are doing is like we are using an ML algorithm that will operate behind it and try to create this new number of samples. Like it can be like KNN algorithm or any other algorithm which can try to create the pattern, try to understand the pattern and create new data points by using this by understanding the hidden patterns within the data, by understanding the hidden patterns and creating this new data to oversample this minority class. So what happens in this case, what is happening is like instead of randomly duplicating the data, we are creating new synthetic data points from the existing data points. So what happens is like it will help us in balancing the data. At the same time, it's not like an duplicating case where we are not trying to we're not trying to overfit the model. So if we duplicate the data, the model will get overfitted. But whereas in this case, what is happening is like as we are creating the features in such a way that it follows a pattern, it will not in most of the cases it will not allow the model to get or to model to overfit. So that's the one benefit of using a smart and I mean synthetic minority oversampling technique or smart. And other techniques are like class weight adjustment, where we try to adjust our class weights in such a way that giving more importance to the minority class, so that algorithm more focuses more upon that particular class. And instead of using this particular I mean instead of dealing this as an classification algorithm, we can also deal this problem as anomaly detection, where we try to understand this particular minority class as an anomaly and try to predict understand the features which will decide the problem, which will decide a transaction as anomaly, which will be further marked as fraud detection. And some of this ensemble techniques can deal with this imbalancedness, but not high. I mean it's better to go with balanced data set, because I particularly face this problem. Even though some ensemble techniques can deal with this imbalanced data sets by default, still it's better to use balanced data like by using this technique, smart or class weight adjustment techniques, so that the model performance will be comparatively better. So now going to approach two, what we do here is we try to create synthetic data from the data that is available here. So for this one, we'll be using a library called imbalanced learn or IMB learn. In this, there are multiple techniques. For this case, we are using minority oversampling technique, which is more. So we are calling that method, and then so we already have our credit card data, and here we are not using the legit data frame, and we are using the original data frame which we created from our data set, and creating our feature data and our target variable data. And then we are running this smart algorithm on top of our X and I mean, our original data. So what happens is like it will come up with new resampled X and feature values, and new resampled class target variable, and then which we can use to train the model. If you look at this one, you can look at the distribution of data here. So now both the classes are balanced, and then we can go ahead and train the model. Similar, I mean, in the similar way which we used to train in our previous case, we are going to train our model by splitting the data set into train and test data set, and then we train the model, And here also we are using the logistic regression model to compare the results. So once we fit the model, we can see our metrics here. You can see that accuracy here is 0.985, whereas for test data, the accuracy in previous case is 0.92. By balancing the data, we were able to increase the accuracy, and that's why we try to focus more upon balancing the data by using oversampling rather than reducing reducing the number of samples. So even you can see this confusion matrix and all. So yeah, now any questions so far in this small technique or not? Now I will give an brief introduction to different classification metrics, and to understand or interpret the results from the report that is available here from the model which we use to predict. Okay, I guess then I will take that as a no. And so it's not just about generating the results. Our major focus will be on interpreting the results and giving business insights to the consumer. So here you can see the classification report it gives us different metrics that are available. It will give us the precision report, precision for different classes, and recall for different classes, and F1 score for different classes, and accuracy for different classes. Here our precision for class 0, which is legit transaction, is 100%. That means whenever there is a legitimate transaction, we were able to predict that legitimate transaction effectively in all the cases, and the model works effectively for any legitimate transaction, and it was able to understand the patterns for every legitimate transaction effectively. And so that means there are no false positives. That means we are not predicting any legit transaction as any legit transaction as this fraudulent transaction. So that means we are doing well in this particular class. And and similarly, where is the recall for this class? Yeah, in case of this precision, you can see that precision for precision for class 1 is 0.09, which is very low because we are unable to predict this particular class effectively, which is very low. Even though our accuracy is 98%, this is what the problem I was trying to explain you. Even though our model is having 98% of accuracy, you can look at the precision for fraudulent transaction, which is very less. I mean, that means we are only correctly predicting 9% of fraud transactions, whereas 99 100% of all the registered transactions were predicted effectively. We are unable to predict these fraudulent transactions effectively because only 9% of this particular fraud transactions are being predicted correctly, which is very less compare and which is very less. And our focus should be on enhancing this particular precision for this class 1, because this of more importance to us, because we don't want to miss any of these. At least even if we miss, we don't want to miss most of the fraud transactions, because if we are predicting only 9% of fraud transactions correctly, then our model is of no use to the consumer. So that's why we try to use different models. We try different algorithms. We try different hyperparameter tunings, and we try, if not possible here, we try some neural networks in order to effectively capture the essence of in order to increase the essence operation of this particular class. So that is one of the major problem with this imbalance data, which can be observed from here. And at the same time, if you look at the recall here, recall is comparatively high here, even for class 1 also 0.89. That what is happening here is that some of the legit transactions are being predicted as a fraudulent transaction, because of which the recall is higher here. But our primary focus is not on recall, because our primary focus is on precision, because we don't want to miss any of the fraudulent transactions. But if you look at this case, even though it is the recall values looks comparatively better, our primary target is not recall in this case because we don't want to miss any of these any of fraudulent transaction. That way, our focus will be on this precision, which is comparatively low for us, and we try to improve. This particular operation for our class one. Even if we see F1 score is nothing but geometric mean of precision and recall, which will bring us to an middle value, normal value of balancing both the cases. Like instead of just focusing on precision or instead of just focusing on recall, we try to come with a balanced way by using F1 score. There are other scores as well, like F2 score or F0.25 score. There are different scores depending upon the coefficient which you use to multiply this, which we calculate the mean harmonic mean value here. So that's how we come with F1 score. F1 score will generally be an better metric to use when compared with accuracy. So even F1 score for class 1 is very less, 0.17. That means the model is not that great. And so we need to do a lot of hyperparameter tuning to enhance the model performance. And yeah, I mean, we already discussed about um, this particular accuracy. Even though accuracy is 98%, the model doesn't make any sense because when it can only predict 9% of fraudulent transactions, that will not be of any use to any consumer. So that's why we don't focus more on accuracy in imbalanced data sets. So the confusion matrix which we are seeing, the true positives and true positives, true negatives, false positives and false negatives. This gives us a brief idea about what is true negative, what is false positive, what is what is true positive, and what is false positive. So this is one important information which you need to have, which you need to by heart, because you can expect a lot of questions in this particular segment. So what here is happening is like true negatives are nothing but if the actual label is negative and the model predicted negative, that transactions are considered as true negatives. True positives are nothing but if the label is positive and the model is predicting positive, those are considered as true positives. Nothing but if a transaction is fraudulent and if the model is predicting fraudulent, then that will become a true positive. And if the model is if the data point is legitimate, and if the model is predicting the transaction as legitimate, then it is considered as true negatives. When it comes to false positives, what happens is false positives are nothing but the legitimate transactions that are being predicted as a fraudulent activity, because here our positive class is nothing but fraudulent class, because we are trying to identify, because we are using one for fraudulent activity and zero for legitimate transaction. So when a legitimate transaction is marked as marked or incorrectly predicted by the model as an fraud transaction, then it will be marked as it will be marked as false positive. When it comes to false negatives, when a fraudulent activity is being considered as, being predicted as legitimate transactions, then that is considered as false negatives. So we need to be more careful in understanding these concepts. And see, if you look at this one, if you look at this, we have around 837 false positives. That means we it is more than the total number of fraudulent data points which we have. That means the model is not performing that effectively. So now what we are going to do is, I mean, instead of using basic logistic regression, what I try to do is I try to use an ensemble method. This method is nothing but random forest. I will explain you how this model algorithm works in next after completing this explaining this notebook. So here I'm using random forest classifier and I'm trying to do hyperparameter. Initially, I tried using, I mean, I wanted to show you different estimators, I mean, different hyperparameters within random forest classifier, but the problem was it is taking a huge amount of time. That is the problem with ensemble method, because it consumed a lot of time. It was taking around more than 1 hour to complete cross validation and to get best hyperparameters. That's why I had to limit to up to only two hyperparameters, which is number of estimators and maximum depth. When you receive this notebook, just uncomment this one and sorry, and then run this model. You can increase this number. You can also add some more values here. Like for example, I used 100 and 200. You can use 250, 300, and 400 as well. Depending if you have, try to do this in Polar notebook, because they will have GPUs and it will be able to complete very fast. So increase the depth up to 30, 40, 50, and 50 and 100, and minimum sample step go up to 50 or 15 or 20. Then you will be able to get best models 6, 8, 10. So you can increase these numbers. It's up to you. You can try this one. If I run this one, it's taking too much amount, a lot of time. So that's why I'm not running here. So when I ran this, as I told you, what grid search CV does is grid search CV try to create combination of all this value. Like for example, if you see, we have 1, 2, 3, 4, 5 values for number of estimators and 5 values for maximum depth, and 4 values for minimum sample split, and minimum sample sleep we have 5 samples, 5 values, and for bootstrap we have 2 values. So it tries to create all the combination of samples along with cross validation steps. So what happens is, like in the first step it will take 100 and 20 and 5, 2 and true. In the next step what it does is 100, 20, 5, 2 false. In the next step what it does is 100, 20, 5, 4 true. 125 4 false. It means it creates different combinations, and the combinations will be around, I mean, for this it will come up to around 200 splits. So roughly it will be getting, you will be running the model 200 times. So you will be training the model 200 times. Yeah, Akshay, please go ahead. You raise hand. If you have any question, please raise your hand. I'm sorry. You can go unmute and you can ask me a question. Is there any question, or by mistake you raise your hand? I will assume that you don't have any question, and by mistake you raised your hand. If you have any question, unmute yourself and ask, or you can drop a message in the chat as well. So it will create these combinations, and in this case, the number of combinations will be roughly around 200 to 250. So that means you are training the model 250 times with different hyperparameters, and you try to come with what is the best performance based upon the metrics which you try to focus upon, and then use that parameters as hyperparameters and finalize the model. So that's what happens in grid search CV. Whereas in this case, I used randomized search CV. What happens in this case is it will not create all the 250 combinations. It will create around 150 combinations randomly, and then it will train the model and try to get the best value within the number of trainings it has done. So in this case, if you look at this case, what is happening is, like I already mentioned you, cross validation, right? So what happens is, like I am giving cross validation as 2. So what happens in case of cross validation is, within the data, within the training data, it will keep some data for validation and then use rest of the data for training, and then cross validate that one, and in the next validation it will use another set of data for cross validation and use this data to use previously use validated data to train the data. So that what happens is, like when some data is not there, the model will understand different pattern, and when some data is not there, the model will understand different pattern. So this every combination, in this case when the cross validation is 2, every combination will repeat 2 times, because we have to validate every combination 2 times. If I increase the cross validation to 5, what happens is, like every combination will be trained 5 times. So that will increase number of iterations that happens while training the model. And you can go ahead and you can, I mean, while using the notebook, you can go ahead and make changes to this cross validation and try to see how the what is the impact on the model. So that will help you in understanding how well, I mean, different different hyperparameters within training the model. So that's how we try to find out the best hyperparameters for this particular model. You can see here how the model trained. So it started. So it's fitting two folds and four candidates, because I used only initially, if you remember this case, I used only 100 and 200 here and max depth as 20 and 30. That means we have four candidates here, four different combinations. So that's why we have four different combinations. And we are evaluating that for two folds. That means every candidate or every combination will run two times. That's why we are having total 8 fits. That means we are training the model 8 times. So that's why you can see here, you can see in the initial combination it used maximum depth as 20 and number of estimates as 100. And the second step also it used the same, but it was a different cross validation. In the other cases, it used 200 as number of estimators and repeated two times because the cross validation number is 2. The attendance link. Yeah. And similarly, it does the same combinations multiple times and it will train the model. And once we have that one, we'll get the best model with us. And then we try to calculate what is the. So this is the best hyperparameters that were found while correcting the combination. And then we can run the classification metrics. You can see here earlier our recall prediction for class 1 was around 0.9 around 9%. But if you look at here, it is around 0.97, which drastically improved the model performance, and the model is performing effectively even in case of this minority class as well. You can see here the false positives and false negatives. Earlier it was 875 and some 87, whereas now the number is reduced to 2 and 23. That means we are making mistakes only in 25 cases out of 2 lakh cases, which is very less. And now we can say like, okay, the model is performing effectively, and now I can be more confident telling that my model can understand the hidden patterns within the data set, that within the data set or within different transactions that come into role in any transaction that come into role in future. So that's how we use an ensemble model and improve the performance. Here, if you say like, do I recommend logistic regression or random forest? Random forest is complex algorithm, and as you saw, I mean, as I already explained you, it takes a lot of time when compared with logistic regression. But here we can't compromise on the performance because the performance difference is very huge. We are getting around 9% correct in case of for fraudulent transactions in case of logistic regression, which is simple regression model. Whereas in case of ensemble model, we are getting 97% of correct predictions correct for fraud transactions. So obviously, even though the algorithm is complex, I had to go with this complex algorithm because the difference is very huge. So that's why we'll be going with this random fast algorithm. And yeah, this is the feature importance I was mentioning. Any ensemble methods like random forest or XGBoost will come with this feature importance option, which will explain. This is like based upon overall data. This is not upon single data point. So it tries to tell you that what is the feature, and for every feature, what is the relative importance in deciding if a particular transaction is fraudulent transaction or legitimate transaction. So if you look at this V17 feature, whatever the feature that is, we can tell like this is impacting the decision this is impacting the prediction significantly in deciding whether the particular transaction belongs to fraudulent transaction or legitimate transaction. And if you look at these other features also up to V11, we can understand like the significance of these features are in most of the cases in these particular V9, V11, V16, V10, V14, V12, V17 features can have a major say in deciding a particular transaction is fraud or not. So we can the consumer can understand like, okay, I think I need to focus more upon these transactions. Like for example, if V11 is some feature, they can control. What they can do is like before the transaction happens, as soon as they look at that one, they can create an inbuilt safety mechanism to deal with this particular feature, and they can control this particular fraudulent transactions. So that's how this feature importance help the consumer or help the user in understanding what makes what are the parameters that will decide if a particular transaction goes, if a prediction happens in that particular way. And the next step, we try to discuss about this sharp plots. I installed this one. Why didn't still not installed? Okay, before this gets installed, so far, do you guys have any questions? So if you don't have any questions, then I will go on. Let's discuss the logistic regression notes I prepared for you. I hope you see this one notebook from my on my screen. So logistic regression, it's nothing but this is generally used for binary classification problem, and we'll be discussing how this algorithm works. Like what is happening behind the algorithm. So when we are training the model, we are trying to understand what happens behind the model. So when we give the data, what essentially happens behind this, it tries to get this particular equation, which is nothing but an regression equation, which we are trying to predict is it tries to tries to find out these coefficients w1 w2 up to wn, where x1 x2 x3 and xn are our features, and use this information to create this equation. And then this equation is applied, a sigmoid transformation is applied on top of this equation to reduce the value to a value between 0 to 1. So ideally, what an logistic regression does is it will predict a probability. It doesn't predict whether the transaction is fraud or not. What it will predict is it will try to predict what is the probability of a particular transaction what is the probability of a transaction to be a fraudulent transaction or to be a legitimate transaction. So ideally, what this say logistic regression predicts is the probability. So in order to predict the probability, what it does is it tries to first estimate the coefficients using our training data, and once it gets this these coefficients from the training data, it generates this equation, and it applies sigma transformation on top of this particular values. Sigma transformation is nothing but if you apply sigma transformation on any value can be reduced to a value between 0 to 1. So ideally, the value which we will be getting after application of sigma transformation is 0 to 1, which is nothing but probability for a particular class. And depending upon the threshold, for example, by default, the threshold will be 0.5. That means if a particular value for a particular transaction, if the probability value will come above 0.5, then the particular class will be marked as fraudulent class or class 1. And if a particular for a particular transaction, if the probability value comes below 0.5, that will be marked as native class or legitimate transaction. So it's not like we have to use this 0.5 as threshold. We can make changes to this threshold, and we can increase this threshold or we can reduce the threshold depending upon our own requirements. So what happens is like we can make changes to the thresholds, and depending upon our problem statements, we can adjust the threshold so that that particular transformation is suitable to our dataset or our problem statement. And while training, the same thing, what happens is like we try to maximize the likelihood estimation to find these coefficients w1 and w2 for each feature, and then we apply log loss or binary cross entropy while doing gradient descent. And then this gives while minimizing this log loss function, we try to get this w1 to w2 and all these coefficients, which will be used to make predictions on top of this data set. And once we have these coefficients, when we get new data set, it will apply these coefficients to the new data, and then it will apply sigma transformation, and then based on the probability, it will decide whether particular transaction belongs to that particular class or not. This particular graph will give you how this transformation works. So if you look at these classes, anything any value that falls beyond this value will be considered as class 1, and any value that falls below this class will be considered as class negative value. So for your convenience, I am giving what is this log loss function. This is the function we try to minimize so that it will try to we try to this value will be used to calculate our coefficients. And in case of logistic regression, we have multiple hyperparameters. Out of them, regularization, solver, and class weight are some of the important hyperparameters. And this regularization parameter is most useful in order to reduce overfitting of the model. And when a model, what this regulation does is, when a model is overfitting, it will try to penalize the complex models. I mean, it will try to penalize the overfitting model and it tries to reduce the overfitting of the model, so that the model, instead of getting overfitted, it will become a normal model and will be more generalized toward the data. So this is about logistic regression. I will provide this one. Go through this one. It might be of helpful to you. And before going to random forest, there is a concept called ensemble models in machine learning, where there will be different techniques like bagging, boosting, stacking algorithms. Bagging, I mean, in case of ensembles, what we're ideally doing is we are taking different models. Let's take a decision tree because we are going to discuss random forest. Decision tree is an algorithm, and instead of using single decision tree, we club predictions from different decision trees and then use the combination of predictions made by different decision trees. This concept works like always. I mean, there's a term, there is a statement called "crowd is always correct." I mean, even this is used in KBC or Kombanega Karopati kind of shows where generally people you will be given a choice to get people from answer response from people, and people will give their votes for different options. And in most of the cases, what happens is, like, it's not all the cases. In most of the cases, when majority of the people vote for a particular response, in majority of cases that response will be correct, because it's like a crowd is always correct. I mean, the statement is like crowd is always correct. And so instead of taking a decision from one person, if we ask thousands of persons, and if thousands of persons will tell the same, I mean, if out of thousand persons, if 900 persons tell like this is the response, then the chances of that response being to be correct is more when compared with taking a response from one or two persons. So that is the concept that is applied here. So we'll be discussing bagging only for this session. So what happens is, in bagging is, here we create a combination of different models, and then take prediction from all these models, and then we try to take majority vote out of the predictions of all these models. Let's take I have 10 models. While creating this bagging model, I took 10 models, 10 decision trees, and 8 decision trees predicted that the transaction was fraudulent activity, and two models predicted the transaction was negative, not a legitimate transaction. So as per the majority vote, obviously the transaction is fraudulent activity. So the final prediction will be fraudulent activity. So it's about like majority voting. When it comes to regression problem statement, I mean, in the case of classification, the majority vote is taken, and when it comes to regression problem, what happens is, like, there we try to take mean value of all the predictions. We have 10 models with us, and 10 models predicted different value. When we have 10 different predictions, we take mean value of all these 10 predictions and then use that value as our predicted value. So that's how this bagging works. So that's how this random forest works. Random forest is one of the bagging model, which is I mean, one of the ensembled bagging model, which uses decision trees as different predictors. So this is how this decision tree looks like. So you have some data points, which will be we have some feature information which will be passed to one decision tree, another decision tree, and like that there will be n number of decision trees. And for each decision tree, the same data sample is passed to all the decision trees, and then a majority voting is taken, and then based upon the majority voting, the final decision is made from this majority voting. But while training, what happens? I mean, this is okay while making the prediction, but what happens in case of training? How does this run? How do you train these bagging models? So what happens in case of training is, like, we create n different decision trees, And what happens is like instead of giving all the data to every decision tree, we give different subsets of data. Like for example, I have 100 data points with me, and from 1 to 50, I take 1 to 1 number 1 rows to 50 rows. To I will take that data and give that to decision tree 1, and I will take data from 20th row to 40th row, and I will give that to next decision tree, and 30th to 70th data to the next decision tree. Like that, I will create different subset of samples, and then pass that subset of data to decision trees, so that they will try to, I mean, each model will train in a different way to make the predictions. So each model is a model in it by its own, and each model was trained in a different way by using subset of different data sets. So what happens is like we have different models. Instead of using single model, we are using n number of models, and then making keeping all these information within these models. And when we are trying to make predictions, we are passing the same information and passing through different models, so that the different models will look at the same data in different way and try to come up with its own prediction. And once each model starts predicting, we try to take majority voting and use that prediction as our final prediction. So that's how this particular bagging algorithm works. And I have given you all this information here. So I mean, bagging can be done in different way. Like for example, I just mentioned you, I will take only few data points. I will pass few data points to, yeah, Pushpanjali, please go ahead. If you are unable to unmute, drop a message here. I will respond to that. Sushmita, can you unmute Pushpanjali? She raised a hand. She has a question.
Yeah, sure, sir.
Pushpanjali, do you have a question?
Yes, they can unmute themselves. They have
Okay.
an access.
Okay. So I think by mistake she might have raised the hand. Yeah. So one way of creating different models is that by using subset of samples data. But there is another way also. Instead of passing all the features, what I do is I will, like we have 30 features in this case. So what I do is I will pass 15 features for first model, and I pass another 10 features to another model, and I pass another 20 features to another model. So we can create change in features also, so that each decision tree will be trained on different types of features, and each model will be unique in its own. So that's why the model will be more effective. I mean, that's why these bagging models will be more effective in making predictions, because we are not just using we are not using one single model. But we are using multiple number of models, which are trained individually and differently on their own by using different data sets and different features. So that what happens is like in most of the cases, a combination of these predictions will be correct. So that's why these algorithms will work effectively. So I'm giving you different hyperparameters here and the significance of them. So what they mean by that. Before understanding that one, I will show you. You might not have idea about decision tree. So decision tree is a machine learning algorithm where the training is done in such a way that when you give data, there will be decision nodes and leaf nodes. Where in decision node, it will make the decision based upon some category. Like for example, let's take fraudulent activity. There is some feature where the transaction distance is 10 kilometers. So it will come with some random split. It will say that okay, if transaction distance between last two transactions is around 100 kilometers, it is a fraudulent transaction, or else it is a legitimate transaction. So here it will create that split, and then but if it's less than 100, it will go to this decision node, and if it's more than 100, it will go to this decision node. And here again, it will take another feature, and it will try to create another split. Like for example, if amount is less than 100 and amount is greater than 100, so again it is creating one more split here, and it will come one more leaf node is coming here, one more leaf node is coming here. So I mean the data is divided among these nodes. So again it will create one more split. Like this, it will try to create splits in such a way that finally you will be having it will come to a position where the final leaf node will be a pure samples. Like for example, all the leaf nodes, I mean the leaf node here should be an pure class 1 or class 0, or this one should be a pure class 1 or class 0, or we can allow the decision tree to have some kind of error with it. When in that case, what happens is like if we tell that we are okay with 10% of margin error, then what happens is like this will go up to 90% of accurate predictions, and then it will stop splitting further nodes. So that's how this decision trees work, and this is called as number of splits, or there are different types of hyperparameters where number of splits, depth of the tree. That means we can how depth it has to go, and all this can be controlled by us by using different hyperparameters in order to control the overfitting. Because if you keep on splitting the features, what happens is it will ideally go to thousands of depth, and there will be thousands of leaf nodes that will be created in order to ensure that every leaf node is pure in the sense it will contain only the data points which belong to that particular class. So which will become like it will try to the model will try to create a boundary which will be like a zigzag node, and it will be overfitting the model. So that is one of the major problems. That's why we never try to go to that extent, and we try to cut the tree to a limited extent and try to ensure that the model is not overfit, and that in order to do that one, we use our hyperparameters. So this is the decision tree how it looks like. I will explain further classes clearly. To understand, to give you a glimpse about what these hyperparameters are, I explained that one. So number of estimators is like how many number of models, individual models you want to train. Like for example, you can train 100 models, you can train 200 models, or you can train 300 models, like that, in order to make predictions. As you increase the number of models, obviously the accuracy in general, the accuracy will be high, because with more number of models, we are bound to have better predictions. And the maximum depth will be the depth of each individual tree or each individual model that we are using in random forest. So what happens is like we can go up to three splits. I mean, we can go up to three individual depth, three trees, or we can go up to 10 trees. We can go up to 20 trees. I mean, it will increase as we increase the depth. What happens is there is chances of overfitting. So we can, by altering this value, we can control the hyperparameters. And minimum samples, like what should be the minimum number of samples for every split. That means whenever there is a split that is happening, so whenever there is a split that is happening here, there should be if I say there should be minimum of 5 samples in each class. That means until unless there are 5 samples in both these classes, it will not split. When it splits, if this node has around only 2 samples, it will not consider this split, and then it will become an leaf node. So that's how this hyperparameter works. And minimum samples in leaf node, and maximum feature that to be used for best bit. I mean, there are different hyperparameters here. You can go through this one so that it will be easy for you. Or if you have any questions, you can ask me in next session. Go through this, and if you have any questions, let me know. I will explain you these individual hyperparameters. I try to make it simple for your understanding. And coming to the different metrics that are used in classification, they focus on this one because they you need to be in a position to answer these things. So you need to understand what is the equation, and what is that particular information, what is this particular equation, what is the information that is being provided by this particular metric. So accuracy is nothing but if you are predicting, you are making total predictions, your total predictions by total number of instances. That means you don't consider false predictions. You take only correct predictions, and then divide it by total number of instances, and get the accuracy. The more important metrics are precision and recall, because instead of focusing upon accuracy, the more focus will be on precision and recall. So precision is a ratio of correctly predicted positive observations to total predicted positive observation. That means true positives are nothing but positives that are actually true and predicted as true. So what we're doing here is we are trying to calculate what is the ratio of true positives to the total positives. That means true positives are positives which are actually positive, and false positives are negative values but incorrectly predicted as false positives. So by this, we are trying to we are trying to understand the precision, and this becomes of more important when the cost of false positives are high. Like for example, if we don't want to predict, I mean, if we don't want to miss any, we don't want to make any false positives, then we need to focus upon improving the patient score, because we don't want to have any incorrect predictions in false positives. So that's why we focus upon precision. Like for example, in case of spam email classification, where we need to focus upon legitimate email, and we don't want to classify any legitimate email as a spam, because if an email is sent to spam, most the chances of losing an important mail is very high when compared with receiving an spam email to our inbox. So that's why here we don't want to make that mistake. That's why we try to improve the precision at the cost of predicting a spam as legitimate email. Similarly, recall is considered as sensitivity, where we try to predict, we try to calculate the ratio of true positives and false negatives. False negatives are nothing but actual positives, but the model is predicting as negative. That means we are missing some of the actual positive values, and we are predicting them incorrectly, and this becomes crucial when false negatives are when the cost of false negatives is high, as I already mentioned you in medical diagnosis cases, where we don't want to miss any of the positive cases. That means we don't want to predict any positive class as negative class, because the cost associated with that class is very high. Because we don't want to miss any patient to any patient miss the treatment because of our incorrect prediction in by our model. So that's why in that cases, what happens is like our primary focus will be on enhancing the recall, even though if we predict some of the negative cases as positive cases. So that's this is how you need to work upon your problem statements. And F1 score is an harmonic meaning of harmonic mean of both this precision and recall. So this will give an more accurate way when compared with accuracy. But remember that precision, recall, and F1 score, all three should be considered while working with classification problems, and look at the information provided by these three to understand the results and while reporting to the consumer. So there is another thing called specificity. So when we want to focus on identifying negative cases particularly, then we use this true negative cases, and we try to focus on specificity. So if our negative is important, then this is the case. So there is another test called AU ROC curve, area under ROC curve. This will give us thresholds and how well the model is performing in for different classes as well as at different thresholds. So I will show you this ROC curve in next session, because we only have 9 minutes now. So I will show you this AUC and ROC curve tomorrow. This is the confusion matrix. True positives is the positive predictions which are actually positives and predicted as positive, and false negatives are actual positive cases but predicted as negative, and false positives are actual actual negative cases predicted as positive, and true negatives are actual negatives and predicted as negative. And there are other metrics as well, Matthews correlation coefficient. They are generally used depending upon problem statements, and not very frequently used, but they are used depending upon your problem statement. So this is about classification metrics. And now let's focus upon the results which we derived from our particular data set. So far, anyone have any questions? I take that as a no. So based upon our classification report, so if we look at this prediction for class 0, which is normal transaction, we have 100% of transactions predicted as legitimate. That means we are doing very good in terms of our class 0, that is which is legitimate transactions. That means when if it's a normal transaction, we will be correct. The model will be correct in predicting it as a normal transaction in 100% of cases. When it comes to recall, where we are trying to predict recall for class 0, we are correct 99% of time. That means we are missing 1% of legitimate transactions, which is going into which is going as negative class, because our model is predicting it as fraudulent transaction. That means we are losing 1% of information into that one. That's why our recall is 0.99. Don't take these values, because this report I used from logistic regression. If we take our, yeah, I will change this and I will provide you. So if we look for operation for our random forest algorithm, it was around 0. Let me see what is the value. It was 0 operation for class 1 is 0.97. So that means 0.97. Let me take 0.97. That means 97% of transactions predicted as fraudulent were actually fraudulent. That means if a transaction is, if 100 transactions are predicted as fraudulent transactions, 97% of them are accurate. Only 3% of the transactions that are predicted as fraudulent were non-fraudulent or normal transactions. So 3% error we can consider, because if we miss a fraudulent activity, we are losing a lot of money. But if we are predicting, we are just stopping the transaction, so that will not cause any major problem to the consumer. So comparatively, this is better. So 97% of operation. Whereas it comes to recall for this class, it is 0.77. So that means when we identify, I mean, 77% of class 1 are already correctly predicted as, we are catching all these 77% of fraudulent transactions effectively. So even in this case also, the model is working effectively, and F1 score was uh, 0.85, which is very good in my observation so far, because getting 0.85 as F1 score is kind of dream to most of the data scientists. And yeah, and even in F1 score is also, our model is doing well. And I need to change this information here, because right now our false positives is very less, I guess. That means uh, what is the false positive? False positives is 2. That means only 2 of our legitimate transactions are predicted as false positives, and when it comes to false negatives, it is 23. I will change this and I will share with that, and model performance metrics we already discussed. So yeah, any questions so far? Tomorrow I will be covering this AU ROC curves, which I mentioned in which I mentioned here, because you need to know what this AU ROC curve is, because you will be getting a lot of questions in this particular segment AUC. AU ROC curves, area under the ROC curve. And another thing I mentioned is, so today I covered logistic regression and random forest, and tomorrow I will try to cover decision trees and support vector classifiers, and we'll be working on time series problem. So we'll work with time series problem and discuss a few more algorithms, and start with if possible, we'll start with neural networks as well. And after that, we'll go with RNNs and natural language processing and CNNs. And the final session will be with respect to language models. So anyone have any questions? If you don't have any questions, then we can drop. Sushmita, shall we end the session, or because I don't find any questions from students?
Yeah, yes, sir. If you're done for the day, we can wind
Yeah,
up
we
the
are done
session.
for the day. I mean, it's only 3 minutes is left, and if we start something else, it will not be better. So let's
Yeah,
end the
no.
session now.
Yeah, we can wind up for the day.
Yeah, sure. Thank you.
Yeah, thank you, sir. Thank you,
Thank you.
students. We'll meet again by tomorrow at 7:30. Thank you, sir.
Yeah, thank you. Have a nice day, everyone.